Hi, I'm Janine Hölscher, and today I will present our work on backward planning for a multi-stage steerable needle lung robot on behalf of a group of collaborators from the University of North Carolina at Chapel Hill, Vanderbilt University, and the University of Utah. Lung cancer is the deadliest type of cancer. It is responsible for most cancer deaths in the US, more than breast cancer or prostate cancer. Early detection of lung cancer, when it is still localized, significantly increases the chance of survival for patients. But unfortunately, imaging techniques such as CT scans can only detect anomalous lung nodules. They typically do not tell us if the nodule in question is benign or cancerous. For a definitive diagnosis, a biopsy is required. There are two common biopsy approaches. In the transoral approach, on the left, the device is deployed through the trachea and into the airways. This is low risk for the patient, but only nodules close to the airways can be reached. On the right, the percutaneous approach is shown. Here, the biopsy device punctures through the chest wall. This provides access to peripheral areas closer to the rib cage, but yields a higher risk for pneumothorax or lung collapse. Our steerable needle lung robot combines the advantages of both biopsy approaches. It is deployed transorally via a bronchoscope, and from the bronchoscope, a steerable needle is deployed that can steer through lung tissue. This provides access to peripheral regions of the lung. The steerable needle has a beveled tip. Through duty cycling, it can be steered along various curvilinear paths, and it can potentially avoid obstacles. Deployment of our robot consists of three stages. First, the bronchoscope is deployed into the airways. Then, the piercing tube is used to pierce through the airway wall and into the lung parenchyma. And finally, the steerable needle is steered through lung tissue and towards the goal while avoiding obstacles. The question I would like to answer today is how to plan the deployment of such a complex three-stage system given a specific goal that we want to reach, which is the nodule in question. In this planning process, we have to consider that each of the hardware stages have their own set of hardware constraints. The bronchoscope can only move inside the airways, and specifically only in airway branches of a certain diameter. Otherwise, it could block smaller airway branches. The piercing tube's deployment orientation can deviate from the bronchoscope's orientation up to a certain angle, and it has to pierce out of the airways and into lung tissue. The steerable needle can follow curves up to its minimum radius of curvature, so this parameter defines the needle's reachable workspace. In the past, to deal with all these hardware constraints, we have chosen a sampling-based approach in robot stage deployment order. We sample a random bronchoscope configuration, then a random piercing tube configuration, and finally attempt to find a plan for the needle from the piercing tube to the goal. If this is successful, then we have found a three-stage plan for the whole system. But more often than not, the goal cannot be reached from this particular needle start pose. And in that case, we have to restart the whole procedure over and over again until we finally find a plan. Our new backward planning algorithm inverts this planning strategy. We start from the goal and plan needle plans towards the airways. When the airways are reached, then we attempt to find a plan for the piercing tube and bronchoscope. Here, in case we are not successful, we don't have to restart the whole planning process. Instead, we keep expanding the needle planning stage and try to connect to the airways until we find a three-stage plan. This leads to a significant speed up. Our planning environment consists of anatomy segmentations from a CT scan. At this stage of our project, we're using pig lungs as an animal model instead of human lungs. We have to avoid collisions of the robot with critical obstacles such as the airways and large blood vessels, and the robot can also not leave the lung parenchyma. In addition, we compute the cost for our plans based on crossing smaller blood vessels. These cannot be completely avoided, but should be avoided as much as possible for safety reasons. We also determine which branches of the airways the bronchoscope can reach, and we represent each reachable branch by a cylinder, here shown in orange. By expanding these cylinders beyond the airway wall, by the piercing tube's length, we also determine the region that the piercing tube can reach when deployed from the bronchoscope. These regions are the targets of our backward planning. Our planning scenario looks like this. We start at the goal and we plan a needle plan from the goal backwards towards the reachable bronchoscope region. To do so, we use an existing steerable needle planner that is based on the rapidly exploring random tree algorithm. We build the tree backwards from the goal, and in this visualization, the little arrows at each tree node represent the needle's deployment direction towards the goal. In each iteration of building the RRT, we create a new random sample. We attempt to connect the sample to its nearest neighbor with a constant curvature arc, and then we take a step along this arc backwards from the existing tree, checking for collisions. And this results in a new node that we add to our planning tree. In our algorithm, we start planning from the goal, which doesn't have an orientation. So with a certain probability, we connect new samples directly to the goal. This leads to creating multiple interleaving trees at the same time. Once a sample reaches the target region, we test if this sample could lead to a full three-stage plan. In this situation, we have a needle plan that leads to the goal, and we now want to find plans for the piercing tube and the bronchoscope. For the piercing tube, we expand the needle plan backwards in a straight line. If it does reach the reachable bronchoscope region, then we check if it lies within the maximum piercing tube deployment angle. If that is the case, we compute a bronchoscope plan backwards from the piercing tube all the way up to the trachea, and we have successfully found our three-stage plan. In our current scenario, though, if we extend the sample to create a piercing tube plan, we see that the piercing tube deployment angle is much too large and not feasible for the device. But instead of starting over, we can simply continue to extend our RRT and add more samples until we find a connection to the airways that adheres to the hardware constraints. Then we have found a full three-stage plan describing the complete robot deployment from the trachea to the goal. Building an RRT in 3D, exploring all directions from the goal, is expensive though. Most of the nodes we add to the RRT, here shown in green, will not contribute to a plan at all. Only a fraction of the nodes actually can be expanded towards the airways, which is the direction that we're interested in. So there's definitely room for improvement here. As a first speed-up strategy, we introduced geometric constraints for new RRT samples. We prune samples that cannot reach any part of the airways because of hardware constraints, because these samples just can't contribute to a plan. A part of the airways, here shown as a brown circle, can only be reached from a sample if all of these constraints are met. First, the distance between the sample and the part of the airways can't be larger than the needle's maximum length. Second, the needle's minimum radius of curvature limits the workspace reachable from a sample. And third, the airways have to be approached from an angle that is smaller than the piercing tube deployment angle. If all three constraints are met for at least part of the airways for a new sample, then we add it to the RRT as a new node. Our second speed-up strategy consists of biasing the growth of the RRT toward the target region. With a certain probability, instead of sampling completely random configurations, we sample from the reachable bronchoscope region. And over time, this leads to the tree expanding into the directions that we're interested in. If we now apply both speed-up strategies to our example and create a new RRT from the goal, we see that the nodes now all could be expanded to reach the airways, and they could potentially contribute to a plan. This makes the RRT creation much more efficient. To evaluate our new algorithm, we have sampled a total of 450 goals in 3 different porcine lung scenarios, 2 ex vivo lungs and 1 in vivo lung. We have attempted to find a plan to each of the goals for 60 seconds. In the evaluation of the simulation, we are interested in which areas of the lung are covered by the different planning strategies. We are also interested in how long it takes to successfully find plans, because time is critical in medical procedures. In the figure on the right, we define success rate as the percentage of goals we found a plan to after a certain amount of time. We start with the prior method, the forward planning. In the figure on the left, the blue goals have been reached, but the black goals have not. After 60 seconds, the forward planner only finds plans to about 50% of the goals, with a standard deviation of 3.9. Even the basic backward planner without speed-up techniques does much better, reaching close to 80% of the goals. Both the target biasing and the geometric constraint speed-up strategies contribute to faster planning and higher coverage. And combining both speed-up strategies for the backward planner results in an over 92% success rate with a standard deviation of 0.4. We also let the planners run in an anytime fashion, such that when they find more plans over time, they also find lower cost plans. This means for any planning strategy, the cost should go down over time. But if we look at the average of best cost plans found over time, the backward planner with speed-up strategies finds lower cost plans much earlier than, for instance, the forward planner does. In conclusion, our new algorithm provides fast planning of low-cost plans, and therefore safer plans, towards most areas in the lung that are reachable by our robotic system. We plan to test our new planning method in an experimental setting with an ex vivo person lung. And with this, I would like to thank you all for your attention, and I'm open to any questions now.